Okay, this is the third lecture of DSP in the series, and the topic is designing of FIR filter using window techniques. Okay, I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC. So, in this particular lecture, we will discuss about the designing techniques in case of FIR filters, and more appropriately, we will focus on the window technique. Okay, so window is the one of the most useful technique for designing an FIR filter. So in our previous lectures, we have seen the designing of IIR filter. So basically, if we'll talk about the FIR filter, so FIR filters, you can say better in terms of designing in case of with comparison to IR filter, because of two reasons. The main reason is that these type of filters are inherently stable filters or inherently stable systems, and also they are having a property called linear phase property, due to which these filters are useful. Okay, so whenever we require linear phase, then we have to go through FIR filters as compared to IR filters. Okay, so let us start with the lecture. So here are the filter designing methods. The filter designing methods, well-known methods of designing FIR filters are basically Fourier series method, and then a window method, then frequency sampling method, and optimum filter design method. So these are mainly four methods which can be used for the designing of FIR filters. But as per our curriculum, we will go through this window method. Okay. So now window techniques. So if we'll see the frequency response of a digital filter, if you'll see the frequency response of a digital filter, then we will find that it is periodic, with period equal to the sampling frequency. Okay, so whatever sampling frequency we will take, according to that frequency, sampling frequency, the spectrum is periodic. So therefore, the desired frequency response of an FIR digital filter can be represented like this. So this is the desired frequency response. Okay, so you can see that desired frequency response is always like we want the response to be obtained, response corresponding to your ideal filter. Means whenever we are talking about desired frequency response, then it should be like for your ideal filter. Okay, so this is the expression hd to the power j omega equals to summation n equals to minus infinity to infinity hdn into e to the power minus j omega n. So here hdn is your desired impulse response, and this is your desired frequency response. So you can say, according to this expression, your desired frequency response is dependent upon desired impulse response. Okay, so because you know the desired impulse response is a discrete quantity, so for the computation of frequency response, we are using here summation sign, and the values are from minus infinity to infinity. That's why summation n equals to minus infinity to infinity. Now, but this hd to the power j omega, you know, in case of a digital filter, or in case of a digital filter, you can say this is periodic with period 2 pi. This is periodic with period 2 pi. So if you see the frequency spectrum, then you will find that it is continuous in nature and periodic with period 2 pi. So this is, you can say, continuous and periodic. Okay, now we want to extract this impulse response from this equation. So we will use hdn equals to 1 upon 2 pi integration minus pi to pi hd to the power j omega into e to the power j omega n. Why we are using integration over here? Because the hd to the power j omega that we are getting is basically continuous and periodic with period 2 pi. So that's why limit is from minus pi to pi, and 1 upon 2 pi is normalizing factor basically. Okay, so here we can see that the Fourier coefficients of this series hdn are identical to the impulse response of a digital filter. There are two difficulties with the implementation of equation 1. Okay, so if you want to implement it, that there are in that case there will be two types of difficulties that we will obtain. Means if our impulse response is of infinite duration, then there are two types of issues that will occur. First issue is that you can see that impulse response is of infinite duration, and second issue that we will consider is that you can see this is non-causal in nature. This is non-causal in nature. So the first, the impulse response is of infinite duration, and second, the filter is non-causal and unreliable. So you can see that if the impulse response is non-causal, then in that case filter is unrealizable. So for making it realizable, what we can do? We can basically delay. We can provide the delay to make it causal, but we can only provide the delay when the impulse response is of finite duration. Okay, so the main challenge out of these two issues, the main challenge is that it is of infinite duration. So if we'll make it of finite duration, then it is easier. Once we will make it of finite duration, then causality is not an issue, because we will provide some finite amount of delay to make the filter causal. Okay, so no finite amount of delay can make the impulse response realizable when the impulse response is of infinite duration. Hence, the filter resulting from a Fourier series representation is an unrealizable IIR filter. Okay. Now, our challenge is to make this infinite impulse response into finite duration impulse response. So, how we can do this? So, here we will choose window technique. So, in the window technique, what we will do basically, we are having infinite duration impulse response, and we will multiply that infinite duration impulse response with a window function, which is a mathematical function, and when we will multiply, then we are having only finite duration impulse response. Okay. So, the finite duration impulse response can be converted to a finite duration impulse response by truncating the infinite series at n equals to plus minus m. Means you can see that if you are having impulse response like this, which is of, you can say, infinite duration minus infinity to infinity. Okay. So, these are the amplitude values, that may be anything. So, this is your desired impulse response, which is extending from minus infinity to infinity. But you are taking some window function like this. If you are having a window function like this, which is extending from minus m to m. Now, you are saying it like Wn. Now, if you are multiplying this Hdn with Wn, Hdn is from minus infinity to infinity, but this Wn is from minus m to m. So, you are having Hn, which is the designed filter impulse response, which is somewhat like this, and you can see here the term will be from minus m to m. So, that is why how we can truncate the infinite duration impulse response into finite duration impulse response by simply multiplying with a window function, and this window function is of finite duration. Here in this case, you can see it is of minus m to m, means n is varying from minus m to m. So, total number of terms in the impulse response will become 2m plus 1, 2m plus 1. Okay. But what happened? If we will simply truncate, you can say if we will simply truncate it using a window function, then what happened? You can see here, but this result in an undesirable oscillation in the pass band and stop band of the digital filter. Why? Because we are truncating the infinite duration impulse response by a window function, which will abruptly truncate this infinite duration impulse response. When the truncation will be abrupt, then in that case undesirable oscillations will be found. So, so this is why it has happened. This is due to the slow convergence of the Fourier series near the point of the discontinuity. These undesirable oscillations can be reduced by using a set of time limited weighing functions, Wn, referred to as window functions. Okay, so what happened? Let's say initially we have not taken any window function and simply we will truncate these values and these values, then in that case definitely there will be oscillations in that case. But what happened if we will choose window function, like in this case, if we will choose a window function wherein the values are within a range, okay, values are within a range and that range is finite. So, we can modify the Fourier coefficients, okay. So, this is due to the slow convergence of the Fourier series near the point of discontinuity. These undesirable oscillations can be reduced by using a time limited weighing function. So, you can say time limited weighing function means the length is finite and it is referred by Wn and called as window functions to modify the Fourier coefficients. Okay. So, now we will see this window technique using a figure. So, you can see this, this is your infinite duration impulse response. You can see dot 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 and dot 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 means n is from minus infinity to infinity. So this is the impulse response of and in this case the impulse response is of infinite duration. And if you will find the frequency response in this case, so you will get this type of frequency response because it is a digital filter. So it will be repeated from minus pi to pi, or it means from 0 to 2 pi it will again repeat it. Okay. Now we have chosen Wn, this Wn as a window function. Okay. So right now I am not describing a particular type of window function, but I am taking a arbitrary window function. So you can see these samples are zeros, and only here you are getting the window coefficients. Okay. So in here you can see the values are in time domain, and here are values in the frequency domain. So you can see here this is the function n and hdn. Now this is n and wn, and now we are multiplying. If we are multiplying hdn and wn in time domain, then we will get the hn. So you can see here wherever these samples occur in window function, you will get the values of these simply by multiplying corresponding coefficient values with this one. Okay. So you are having this type of impulse response. Similarly, if you will see, if you will take any window function, then its frequency response is somewhat like this, which is a type of sinc function you can say. And when you have truncated infinite duration impulse response by window function, then you will have a impulse response which is finite duration, for which you will get this type of frequency response. Okay. Now, if you want to realize, because we want to realize the FIR filter, so what happened? Because you can see this is non-causal in nature, so we can make it causal. Now, right now we can make it causal by providing a delay of n units in time. Okay. So if you are providing a delay of n units in time, then this sample will start from here, and you are having, let's say we are calling it as Gn. Okay. So this is a finite duration impulse response having 0 to m minus 1, means total number of m terms, and you can easily realize it. Okay. So this is how we will obtain the impulse response, finite duration impulse response, which is basically for which we can do the designing, or based on which we can obtain the design of an FIR filter. Okay. So the Fourier transform weighing function consists of a main lobe which contains most of the energy of the window function, and side lobes which decay rapidly. So here you can see this is the frequency response of the window function. So you can see this is the main lobe. If you will see, this is the main lobe, and others are side lobes. So this main lobe is very important because all the energy should be concentrated in this particular main lobe, and these side lobes should not be there. And these side lobes are basically the spectral leakage. So we want to choose such a window function wherein the most of the energy is concentrated in this main lobe, and these side lobes are almost negligible. Okay. This sequence Hn equals to Hdn into Wn is obtained to get an FIR approximation of Hg to power j omega. The sequence Hn is exactly 0 outside the interval minus m to m. So here we can see this. This is basically 0 outside this interval, and the sequence Hn and its Fourier transform h e to the power j omega are shown in the third row. H e to the power j omega is nothing but the circular convolution of h e to the power j omega w to the power j omega. So here we can see that here we are doing the multiplying operation, so that we are getting this, and here in frequency domain, you know, in case of the time domain, the multiplication in time domain corresponds to convolution in frequency domain. So you can say this and this will make a convolution of these two, will get the final frequency response. Okay. The realizable causal sequence Gn, which is obtained by shifting Hn, is shown in the last row, and this can be used as the desired filter impulse response. Okay. So now we can choose this causal impulse response for designing of a FIR filter. Now, a major effect of windowing is that the discontinuities in h e to the power j omega are converted into transition bands between the values on either side of the discontinuity. So you can see that what happened when we are choosing a particular type of window function. In that case, we are having these side lobes according to the shape of the window function. If the window function chosen is like somewhat of rectangular shape, so it is nothing but you can say it will abruptly truncate this infinite duration impulse response. So in that case, the you can see these frequency response will consist of you can say more number of side lobes. And if you are having a truncation which is gradual truncation, like if we are having window function like this, so you can see the truncation of this infinite duration impulse response is more gradual. So if it will become more gradual, then in that case, what happen? Number of side lobes are less, but you will find that the main lobe width will become increases, and that is nothing but this main lobe width is nothing but the transition bandwidth. So if you are trying to truncate infinite duration impulse response by a window function which is by which the truncation is gradual, then in that case you can say transition bandwidth get increases. Okay, so if you are having some advantage of lesser number of side lobes but at the cost of increasing transition bandwidth. Okay, so the width of this transition band depends on the width of the main lobe of frequency response. A secondary effect of windowing is that the ripples from the side lobes of W power j omega produces approximation error for all omega. So this I have already based on the above discussion, the desirable characteristics be listed as follows. So what should be the desirable property of window function? So the Fourier transform of the window function should have a small width of main lobe containing as much as of the total energy as possible. So here we can see that we want that the width should be smaller and smaller possible, and height should be as large as possible. Okay. Then second is the Fourier transform of the window function should have side lobes that decreases in energy rapidly as omega tends to pi. So we want that the energy within the side lobes should be you can say should be like this, that the width of the major lobe should be as small as possible, and number of side lobes should also be decreased. Okay, so here are some of the window functions that can be used as a window function. So the starting one is the rectangular window function. So in each and every window function we are having two types of category. One is causal window function, another one is non-causal window function. So here we are considering non-causal case. In case of non-causal, we are assuming that it should be symmetric one. Okay, so we can see this is the window function for symmetric rectangular window function. So within this range minus n minus 1 by 2 to n minus 1 by 2, the window function value is 1, otherwise 0. Okay, and in case of causal, you can see the limit is from 0 to n minus 1. Okay, total number of terms are here n, and here you can say again here n. Okay, n minus 1, and one value is the center, so it will become total n, and here also total n. Now because we know that by rectangular window, if you will truncate the window the infinite duration impulse response, then it is like just like we are doing it abruptly. Okay, so number of side lobes are more here. So so now the solution is that we have to choose some window functions like that, wherein truncation is not abrupt but it is gradual. So for starting that, first window is the modified rectangular window function. So what happened? It is just the modification of rectangular window function, wherein we have put first value and last value of the window function sample is equal to half. So here we are choosing W0 equals to Wn minus 1 equals to half, and all other values are 1 within this range. Okay, so we will get a response somewhat better than that we have obtained using rectangular window. Then another window function that is used is Hanning window function. Again causal and symmetric you can see. So, so in this case, causal Hamming window, you can see the coefficient is 0.5 minus 0.5 cos 2 pi n upon m minus 1, where n is between 0 and m minus 1. So, by this window function, we can calculate the coefficients of a causal Hanning window function. And for non-causal case, non-causal means symmetric case, rather than using this plus sign, we will use this plus sign. And this time the range is from m minus 1 by 2 minus of m minus 1 by 2 to m minus 1 by 2, because mod n sign is there. And you can see the width is main lobe of approximately is 8 pi by m. Okay, later on we will see the comparison also. Then Hamming window function. So Hamming is just modified. You can see in Hanning window function, first and last sample value is 0. Okay, so effectively only m minus 2 terms will be there. So that modification is done by this Hamming. And in Hamming window function, the coefficient values are adjusted, like 0.5 is replaced with 0.54 and 0.5 is replaced by 0.46. So you can see now the first and last sample values are not 0, but it is equal to 0.08. So this is the case of causal Hamming window function, and this is the case of non-causal or symmetric Hamming window function. Again, the same thing is there. Okay. Then the Blackman window function. So you can see Blackman has found that the number of side lobes can be significantly reduced if we will use an extra cosine term in the window function. Okay, so this extra term will be added by the Blackman, due to which side lobes can be reduced significantly. Okay, so this is the example of non-causal window function, and this is the example of causal Blackman window function. Okay, and width of the main lobe is approximately 12 pi by m. So you can see width of main lobe becomes increasing as we are moving. Okay, then last one is the Bartlett or triangular window function. Okay, so in triangular window function has been chosen such that it has tapered sequence from the middle or either side. The window function Tn is defined as. So we can see that it will truncate very gradually the infinite duration impulse response, and you can see the window function formulas are like this: 1 minus 2 mod n upon n minus 1. For n is for small n lying between minus n minus 1 by 2 to n minus 1 by 2. And similarly for causal, it is like this. Okay, so by this we can use by this we can use the window function of Bartlett triangular window function. Okay, so this is the window function. So we can choose any window function for obtaining the frequency response of a FIR filter. But as you will see, as the window becomes more gradual, then in that case, what happened? The width of the main lobe is more, but number of side lobes are reduced. But the width of the main lobe can be controlled by increasing the filter order. You can say here the width is 8 pi by n. It means if you increase the value of filter order, then what happened? Your if you will increase the filter order, or you can say length of the window function, then this width will become reduced. So you can say it will be inversely proportional to the length of the window function. Okay, now we can see here is the comparison among different window functions. So you can see here in case of rectangular, this is 4 pi by m, and Bartlett 8 pi by m, Hanning 8 pi by m, Hamming 8 pi by m, and Blackman 12 pi by m. So from here we can see the width of the main lobe is higher in case of Bartlett window function and smaller in case of rectangular window function. But at the same time, if we will see this minimum stop band attenuation, so it is the minimum here and it is the maximum here. So it means we are getting the response in which from Blackman window we are getting the response in which number of side lobes are very less, but transition bandwidth for same filter order is same. Okay, so this is the comparison you can see also from here. So this is for rectangular, and this is for Hamming, Hanning, Bartlett. Okay, so this is the comparison basically. Okay. Now, design of a FIR filter using windows. So here we will see that how we will design a window, design an FIR filter using window technique. So first of all, we will choose the desired frequency response. Then we will take the inverse Fourier transform to get infinite duration impulse response. Then we will multiply it with window function to obtain designed filter impulse response, and then we will obtain the transfer function by taking the jet transform of impulse response. So here we can see one of the numericals I have taken. So here we can see that frequency response is e to the power minus j2 omega between minus pi by 4 to pi by 4. So you can see this is a low pass filter because the values are like this. Okay, so this is, we have to design here a low pass filter. So here in this case low pass filter, and you can see here e to the power minus j omega alpha term is there. And you can say this delay is due to its causal nature. So we have to choose a causal window function for the designing of this filter. Okay, so this is hd to the power j omega. Then we will take the we will calculate hdn by taking its inverse Fourier transform. So 1 upon 2 pi minus pi to pi, and then we will solve it. Now this is for minus pi to pi, but our pass band is restricted to minus pi by 4 to pi by 4. So limit will be minus pi by 4 to pi by 4. Then we will solve it. So finally we will get this value 1 upon pi n minus 2 sin pi bar and sin pi by 4 n minus 2. So this is the value of hdn. Now we will calculate the value of hdn at different values of n from 0 to n minus 1, and the length of the window function is given as here 0 to 4. So we will calculate HD0, HD1, HD2, HD3, HD4. But because we know the FIR filter, it is having linear phase property, so there is no requirement to calculate all these values. We will only calculate 3 values, and other values are like HD0 will be equal to HD4 in this case, and HD1 and HD1 will be equal to HD3. Okay. One important thing while calculating is this: when we will calculate n at center value, like n here, capital N is 5, so n will become 2, so it is the center value. So at center value this will become 0 by 0 form. So we cannot directly calculate the coefficient value, but we will apply L'Hopital rule in numerator and denominator and then put n equals to 2. Okay. So here we have calculated the coefficients. You can see that HD0 equals to HD4 equals to 1 upon 2 pi, and HD1 equals to HD3 equals to 1 upon under root 2 pi, and the center value. How we have obtained the center value? We will take we will do the differentiation in numerator and denominator and then put n equals to 2. So we will get this value HD2 equals to 1 by 4. Now we will calculate the window coefficient. So here we are using as per this function. This is the function of rectangular window. So we are using a rectangular window function. So in rectangular window function, all the coefficient values are 1. So you can say Wn equals to 1 for all n. Okay. So W0 equals to 1, W1 equals to 1, W2 equals to 1, W3 equals to 1, W4 equals to 1. So whenever we will multiply it with HD0, HD1, HD, so we will get this same value. So here, because this value is 1 for each and every sample, so whatever the values we have obtained for HDN, we will get the same values for HN. So similarly, H0 equals to H4 equals to 1 upon 2 pi, H1 equals to H3 equals to 1 upon under root 2 pi, and H2 equals to 1 by 4. So this, why these are equal? I have already told this is equal because of the linear phase property of FIR filter. Okay. Now these are the coefficient of the designed filter. Now we will use this coefficient to obtain the frequency response of the designed filter. So the frequency response is given by, this is the expression, n equals to 0 to n minus 1, which is equal to 4 Hn into e to the power minus omega. One important thing that you have to keep in mind, that your impulse, the desired the frequency response should be causal. So for making it causal, we will take the term of e to the power minus j omega alpha, where e to the power minus j omega alpha outside, where alpha equals to n minus 1 by 2. Here n equals to 5 minus 2, that will become 2. So we will take this term outside. So that's why after expansion of this, we have written it like this. Okay. Then we will take e to the power minus j 2 omega term outside, and then accordingly we have converted these values, h naught e to the power 2 omega, h1 e to the power j omega plus like this. Then what we will do, basically we will take, now you know that h naught will become h4 and h1 equals to h3. So accordingly we have taken these values, accordingly we have arranged these values, and then we have put the coefficient values. And you know e to the power j 2 omega plus e to the power minus j 2 omega is nothing but 2 cos 2 omega, and this term is 2 cos omega. Okay. So this will become 2 cos 2 omega, then it will be cancelled out. So it will become 1 by 4 plus 1 by plus root 2 upon pi cos omega plus 1 by pi cos 2 omega. So this is the frequency response. If you want to calculate the jet transform, or if you want to calculate the transfer function, then simply Hz equals to summation n equals to 0 to n minus 1, it means 4 Hn into z to the power minus n. Now if you will expand it, you will get the value of you will get the transfer function for this particular filter. So transfer function and the frequency response, there are two things that you have to calculate while designing the FIR filter. Okay. And so these are the references that I have taken for my presentation, and thank you. Thank you, sir.